Hello differential equation students. In this video, let's take a look at how do we make use of this formula. It's called the derivatives of Laplace transforms. We already did how does the Laplace transforms work with the derivatives. We already know the Laplace transform of the derivatives. What do I mean by that? By which I mean L of f prime of t. This is the Laplace of the derivative. We are not going to do that in here. What we are going to do it in here is how does the derivative of the Laplace, right? This is the Laplace transform and here's the derivative, right? So this is the derivative of the Laplace and how do we work with that? So here's the formula. The formula is the Laplace of Laplace of f of t is equal to cap f of s, then Laplace of t to the n f of t. Every t that you multiply with the f of t before you taking the Laplace, then what do? It will be same as finding that many derivative of the Laplace transform, and you multiply that by -1 to that many t's that you multiplied with the f of t. Let me give you one simple example and then we will move on. So for example, I will give you the simpler one before we take a look at this example. Suppose if I ask you what is the Laplace of t e to the 2t, right? What would that be? T to the 2t. Since t is multiplied with the e to the 2t, right? What we are going to do is first we are going to find the Laplace of t e to the 2t, Laplace of e to the 2t, and then we are going to find the derivative of that with respect to s and then multiply -1 to the n. N in this case is the power of the t, which is 1, so that's going to be simply 1, right? So if I do that, what's going to happen? Then you would see that this is -1 times the derivative of whatever the function we're going to get in a moment with respect to s, right? When I do that, we know that derivative of Laplace of 1 over e to the 2, Laplace of e to the 2t would be 1 over s minus 2. And if I find the derivative of this, you all know this would be -1, and this is this would be -1 times s minus 2 to the -2, and if you simplify, this is going to be 1 over s minus 2 the whole squared, right? And that is that one. And by the way, we can use the formula that we just learned in the previous video, which is this one right here, right? The translation, the first translation formula, and there how these things moves, right? When we multiply e to the at, when we multiply e to the at with the f of t, then what do? You replace the s by s minus a, right? And I can apply that also in here. Let me change the color. If I apply that, then what's going to happen in this? So this would be, now we are looking, this is L of Laplace of e to the 2t multiplied with the t, and if I use the first translation theorem, this would be Laplace of t and replacing t by s minus 2. Laplace of t, you all know this is 1 over s squared, and you replace the s by s minus 2, then that's going to give you 1 over s minus 2 the whole squared. And you see that these two are, these two should be, that's mathematics, right? These two are exactly one and the same, and so we can use either way. It doesn't work in every single cases, since the problem that I showed here was e to the 2t. It works nicely, but it doesn't work like that in every single case. All right, now having done this problem, now let's take a look at how do we solve this one. The idea is very simple, just like we did. Since there is a t being multiplied and the power being 1, the Laplace of this would be -1 raised to the 1 times the derivative of the Laplace with respect to s, the Laplace of sine 3t. I'm going to skip that step, and so we know that Laplace of sine 3t is going to be 3 over s squared plus 9. We all know that very well, right? And that's it. And that's it, right? Now all we need to do is to find the derivative. If I find the derivative, ladies and gentlemen, you would agree with me, this is going to be -1 times this is 3 times s squared plus 9 to the negative. I'm using a chain rule and power rule, right? Minus 2, there is another negative 1 times the derivative of that, which is going to be 2s. And if I simplify all that, you will agree that I'm going to have 2 times 3 times s, and the whole thing is divided by s squared plus 9 the whole squared. The very important aspect here is, you know, this s squared plus 9 the whole square. Again, this may not be, you know, this might be easy, but what is very important, this one is the Laplace inverse. The Laplace inverse is very, very useful in these things, right? So now what I have is, you know, Laplace of t sine 3t equals 2 times 3s over s squared plus 9. So what is the Laplace inverse of this? Which should be that right there, right? And that's what we're going to make use of in the next problem when we solve this. By the way, in general, if you want me to, you know, generalize this, we can generalize this as a formula in this way: the Laplace of, in general, t sine kt, for whatever the constant k, that would be 2ks, and the whole thing is divided by s squared plus 9 the whole squared. So when you see something like this, then you know that the Laplace inverse of this is going to be this right here, right? And that's what we're going to use in this problem when we solve it. Let's take a look at this initial value problem. And by the way, for those who paid attention to the applications, this problem comes, you know, from an undamped mass spring, right? Mass spring problem, right? Here the initial velocity, the y prime of 0 means that is the velocity is equal to 1, right? 1 feet per second, if you want to think of it that way. And y of 0 equal to 0, that means it's in the equilibrium position. The spring is in the equilibrium. So if you remember the spring, right, and there's a mass over here, right, and the spring is in the equilibrium position, and it is released, you know, as the velocity is 1 feet per second, if you want to think of it this way. And there's an undamped one, and there's, you know, the spring mass problem, right? This is a spring mass problem. If you think of this as a modeling, coming off of some modeling right here, right? All right, so if you do that, now let's see how do we solve it. Again, for those who don't know, go back to the chapter 5 and take a review those problems. You will see why this is a modeling coming off of this mass spring problem. All right, now let's take a look at how do we solve this one right here. We're going to use the Laplace in here to solve it. So the same technique, the same idea that we have been using all along, that I've been kind of saying over and over again. So we're going to use, you know, this particular process that we have been following for a while, right? We're going to use the same particular process that we have been following for a while. We have a differential equation in terms of t, and then transform this into algebraic equation in terms of s, and solve for s, y of s, and then using the Laplace inverse get the y of t. Let's do that. The step 1 is we're going to plug in. We're going to apply the Laplace transform. I'm going to say simply LT in here. If I do that, ladies and gentlemen, then this would be Laplace of y double prime plus 9y as a functions of t, by the way, as functions of t, is equal to Laplace of cosine 3t. And again, using the linearity property and using the Laplace of the derivatives, then the first one, right, this one is going to be, let me change the color, is going to be this right here, is going to be s squared cap y as a function of s, by the way, minus s times y of 0, and then minus y prime of 0. And let me change the color, and if I apply the Laplace on this one, that's a very simple one. It's going to be 9 times s times the cap y. No, there's no s times, that's just a function itself, right? So there is no derivative, so it's simply 9 times y, and this is going to be equal to Laplace of cosine 3t. And the Laplace of cosine 3t is, you all know that Laplace of cosine 3t is equal to, it's a 3t, it's a cosine, so I'm going to have s on the top. I'm going to have s squared plus 9 on the bottom, right? That is what we are going to have. Now let's see how do we solve this. So we got a now algebraic equation in terms of the cap y. We're going to solve this for cap y, right? So that's my next step. If I do that, then I'm going to group all the terms with respect to y, cap y. Then I'm going to have s squared in here. Then I'm going to have a 9y, and then I'm going to have a 9y there. So this is going to be s squared plus 9. And y of 0 is 0. This is a history, it's gone. Y prime of 0 is equal to 1, so this is equal to 1. So I'm going to have a plus 1 there, so minus 1 there. And when I move to the other side, right, then this is going to become a plus 1. So when I'm going to move this to the other side, it's going to become a plus 1. Let me do that. When I do that, this is going to be 1 plus half of that, right? And that's what we have right there as the y. I still have not solved it. I'm still working on it, right? So now what I have is I have a cap y, which is equal to 1 over s squared plus 9, 1 over s squared plus 9, and plus s over s squared plus 9 the whole squared, right? Now how do I solve this particular one, right? And you see in this particular one, this resembles something like this, right? Except we don't have the k in here, right? If I had a 9, and by the way, this should not be a 9, this should be a k squared. So this is a 9, right? So which means that, you know, I need a 6 on the top. I would like to see a 6s on the top, but I don't have a 6s. I have only s. That's not a big deal. You know, we know how to manipulate this, right? All right. So now we know the Laplace inverse. By the way, what is the next step? The next step is to find the Laplace inverse, right? So we are right here. Now we are in this step. We found the solution. I'm looking at how do I do my next step, which is to find the y of t. I need to apply the Laplace inverse. That's what my goal is. That's what I'm looking at it now. So let's take a look at this and then see what can we do in here. So the next step 3 is applying Laplace inverse transform. Let's split it up. Then this is going to be y of t. Let me write it down. Let me write down the steps. So it's going to be Laplace inverse of cap y on my left hand side, which is Laplace on the right hand side is going to be Laplace inverse of 1 over s squared plus 9, which we will know in a moment. That's an easier one. And then I have Laplace inverse of s over s squared plus 9. All right, so now if I pay close attention to this, there is not really a direct Laplace inverse for this, and so is for this, right? So we're going to do some algebraic, or in this case numerical or algebraic manipulation in here. Because of that reason, let me let me just move it up right here, so you know it's easier for us. All right, so if I had a 3, if I have a 3 in here, then that's actually looks like sine 3t, right? So to have a 3, I need to multiply by 1 over 3. Same thing in here. By looking at this, if I had a 6s on the top, then that I know what to do. So I'm going to multiply 6s in here, 6 in here. So you have to divide by 6, right? And then we are done. And now I can do all that wonderful things. So if I do that, my solution would be y of t is equal to 1 over 3, and Laplace inverse of a constant is on the top, so it's going to be sine 3t plus 1 over 6. And again, if I apply the same formula that we had right here, right, if I apply this right here, here you see my k is equal to 3, my k is equal to 3, therefore this would be t sine 3t for my k. So this would be t sine 3t for as my solution. So this is much simpler. This is much simpler than doing, you know, the other methods. But of course, you know, you should know how to work with Laplace in this case. And that's how we solve this problem. Not only solved it, just some any differential equation. As a matter of fact, this differential equation, as I said earlier, coming off of mass spring, undamped mass spring problem. So now you know how to work with suspensions theoretically, right? We know how to with even now we also know how to simulate suspensions theoretically, yeah, and then we know how to solve them using Laplace transforms this way. So I'll stop the video right here. In the next video we'll see how do we use the Laplace to solve more differential equations. The next video we're going to take a look at solving the systems of linear differential equations, and then we will do more.